Hello everyone. Tonight we dive deep into stars we have never seen before and exactly what scientists know about them. Now, dim the lights and let's ease into tonight's journey together. The universe, as vast and ancient as it is, has always operated under a set of observable patterns. Gravity shapes galaxies. Nuclear fusion powers stars. Time warps near mass. These are the laws we've painstakingly pieced together over centuries of observation and mathematics. And yet, some stars, enigmatic, silent, distant, seem to disregard these rules altogether. These aren't just rare anomalies. They are profound disruptions to our understanding of reality. They challenge our models of physics, thermodynamics, and stellar evolution. They aren't just oddballs. They're indicators that we're missing something crucial. Stars, in their classical sense, follow a well-mapped journey. They are born in dense clouds of gas, ignite through nuclear fusion, live out lifespans based on their mass, and eventually die as white dwarfs, neutron stars, or black holes. That's the roadmap. But what happens when a star doesn't follow the map? Our story begins not with a bang, but with a flicker. An irregular dimming that captured the attention of astronomers not because of what it showed, but because of what it didn't. In 2015, the world met a star that defied expectations. KIC 8462852, later nicknamed Tabby's star. It was discovered through data collected by the Kepler Space Telescope, which monitored thousands of stars for periodic dips in brightness that might indicate orbiting planets. But Tabby's star did something far stranger. It dimmed, and not just once or regularly like a planet transit. It dimmed by as much as 22% and then brightened again unpredictably. No known exoplanet could account for such irregular, extreme behavior. Dust was considered, but the light patterns didn't match. Astronomers proposed comet swarms, giant ringed planets, or even alien megastructures. The scientific community bristled at that last suggestion, but the data was undeniable. This star was doing something no star should. Tabby's star became the face of a new mystery. Stars that don't act like stars. And it wasn't alone. As instruments like Kepler, TESS, and Gaia have peered deeper into space, they've uncovered a growing list of stellar rule breakers. Objects that pulse at impossible intervals. Stars that seem too old for their surroundings. Bodies so massive and cold they blur the line between planet and star. There are stars emitting radiation they shouldn't have the energy to produce, and others that appear to disappear entirely for years before reappearing like celestial ghosts. Consider J05311, a star discovered in the constellation Cassiopeia. It radiates infrared light with such intensity that it was initially mistaken for a black hole accretion disk. But it had no companion, no disk, just itself, burning at an unexplainable rate. Astronomers now suspect it might be the result of two white dwarfs merging into a new, reanimated object, a kind of zombie star, reborn from the dead. Then there are stars that shouldn't exist because of where they are. In the galactic halo surrounding the Milky Way, stars like HE 1327 to 2326 have been discovered with such low metal content that they appear to predate nearly every known generation of stellar formation. These are stars with almost no heavy elements, no iron, no carbon, no oxygen, suggesting they were born directly from the ashes of the very first stars in the universe. The fact that they are still burning contradicts models that say such low metal stars should have long since faded. One particularly intriguing class of objects are the Thorne-Jitkov objects, a bizarre hybrid predicted by theory but barely evidenced in observation. These are stars with a neutron star core inside a red supergiant envelope, essentially a neutron star that has merged with a normal star, creating an object with chaotic nuclear processes and strange spectral signatures. We think we may have spotted one or two candidates, like the star HV 2112, but they're almost impossible to confirm. Still, the physics of such a configuration shouldn't work, yet the light we receive says otherwise. What links all of these cases is a sense of disobedience. These stars are refusing to fit into the categories we've built. They're the kind of cosmic glitches that make theorists uneasy and observers obsessed. But why do these stars matter? Because when something doesn't fit, it's not a nuisance. It's a clue. It's a whisper that says, your model is incomplete. And in astrophysics, those whispers often lead to revolutions. Before we understood the structure of the atom, radioactivity didn't make sense. Before Einstein, the orbit of Mercury was an unresolved anomaly. Before quantum mechanics, black-body radiation was a paradox. And today, these stars, these rogue, luminous bodies drifting through our galaxy, may hold the key to the next big leap in our understanding. They may tell us something about the early universe we've missed, or about exotic forms of matter we don't yet understand. Some might even hint at entirely new laws of physics, or bridge the gap between gravity and quantum mechanics. But first, we must listen to them. Modern astronomy is undergoing a silent revolution. With high-resolution spectral data, precise parallax measurements, and continuous time series analysis, we're entering an era where the universe is revealing its hidden misfits. These misfits, once brushed off as outliers, are now the main focus. And as we examine these strange stars more closely, we find ourselves confronting questions that sound almost philosophical. What does it mean to be a star? Can fusion exist in forms we haven't imagined? Could some stars be powered by dark matter annihilation or exotic particles that defy the standard model? Are we even looking at stars or something entirely new? With every unexpected dimming, every spectral anomaly, and every gravitational oddity, we are being invited to rethink what we know. Not just about stars, but about the universe itself. Some stars follow the rules, others rewrite them. Tabby's star and the rise of the inexplicable. When astronomers first turned their attention to KIC 8462852, now famously called Tabby's star, they didn't expect to uncover one of the most baffling celestial mysteries in modern history. It wasn't brighter than others. It wasn't closer or larger. It simply behaved wrong. At first glance, Tabby's star seemed like a standard F-type main sequence star, roughly 1,470 light-years away in the constellation Cygnus. But as Kepler recorded its light over 4 years, something stunning emerged. Massive, irregular drops in brightness. These dips weren't the subtle dimming caused by a passing planet. They were erratic, dramatic, some as deep as 22%, far too extreme for anything conventional. To put that into perspective, if a planet the size of Jupiter passed in front of a sun-like star, it would block about 1% of the light. Something blocking 22% would have to be absolutely colossal, or an ensemble of objects working together in a bizarre formation. But even that didn't explain the randomness. The dimming occurred without periodicity. Sometimes it would drop sharply, other times gradually. Then the star would return to normal, only to plunge again days or weeks later. The astronomical community erupted with speculation. Could it be a swarm of comets? A massive cloud of interstellar dust? A planet with an enormous ring system like Saturn on cosmic steroids? Every answer led to more questions. None of these ideas fully fit the data. Dust, for instance, should scatter different wavelengths of light in a measurable way, but that wasn't observed. The dips weren't wavelength dependent. The light was dimming evenly across the spectrum, hinting at a solid object or uniform material. And then came the more audacious theories. A Dyson swarm, not a single structure, but a constellation of energy-harvesting machines built by an advanced alien civilization. It wasn't a mainstream scientific conclusion, but it gained traction simply because every natural explanation seemed to fall short. It was less about believing in aliens and more about acknowledging the sheer strangeness of what we were seeing. Even the SETI Institute pointed radio telescopes toward Tabby's star to search for unnatural signals. They found nothing. No pulsed transmissions, no structured patterns. Silence. Just a strangely dimming star and a universe of confusion. Years later, more detailed observations would provide a partial explanation. Long-term monitoring by ground-based telescopes like Las Cumbres and photometric campaigns suggested that some of the dimming events were consistent with orbiting dust, possibly from a disrupted exomoon or a disintegrating planet. But the mystery remains unsolved. The patterns are still irregular. The nature of the obscuring material is still unknown. And most of all, Tabby's star sparked a new class of inquiry. What else is out there that doesn't play by the rules? And indeed, once astronomers knew to look, they started finding more. Another perplexing case arose with the discovery of EPIC 2042789116, a young star located about 440 light-years away in the Scorpius-Centaurus association. This star, too, exhibited massive dips in brightness, up to 65%, and again, without a consistent rhythm. The favoured explanation was that this young star was surrounded by clumps of dusty material from a forming planetary system. But even then, the models strained to explain the depth and duration of the dimming. Suddenly, the idea that erratic light curves meant alien megastructures became a distraction from a bigger revelation. That our understanding of early stellar systems, planetary debris, and stellar environments might be incomplete. That many stars might be surrounded by structures or phenomena we haven't fully accounted for. Not because they're exotic or artificial, but because they reveal parts of stellar evolution still cloaked in mystery. These discoveries also raised another question. How many of these anomalies have we missed? Kepler, for all its precision, only stared at a small patch of sky. It collected data on around 150,000 stars. But the Milky Way holds hundreds of billions. What if Tabby's star wasn't rare at all? What if stars with complex dimming behaviors were common, but simply hadn't been noticed because we hadn't looked long enough, closely enough, or in the right way? This has motivated new missions to monitor stars for extended periods with greater sensitivity. The Transiting Exoplanet Survey Satellite, TESS, the Vera C. Rubin Observatory, and even the James Webb Space Telescope all contribute to this expanded search for anomalies. Not just planets, but phenomena. Not just explanations, but provocations. One of the most important takeaways from Tabby's star was philosophical. That certainty is dangerous in science. That when we expect stars to act like stars and ignore data that contradicts those expectations, we risk blinding ourselves to discovery. Because the light from Tabby's star told a different story. One of chaos, not order. Of shadows without clear sources. It challenged not just astrophysical models, but the scientific instinct to categorize. And beyond the science, it ignited the imagination. Artists and authors dreamed of Dyson spheres and alien civilizations living under artificial night. Scientists debated the boundaries between speculation and rigor. The public rediscovered the thrill of cosmic mystery. Perhaps most compelling is what Tabby's star symbolizes: a quiet rebellion. A single point of light among billions that refused to behave. And in doing so, it reminded us that the universe isn't a solved puzzle. It's a living question. There's a kind of poetry to it. A faraway sun flickering without explanation. A riddle that resists closure. A cosmic lighthouse signaling that there's more to learn. And as our instruments sharpen and our patience deepens, we begin to uncover not just more stars like Tabby's, but a broader pattern. Stars that rotate too fast, stars that grow younger, stars that produce unexplained radio bursts, and stars that seem to change their temperature over decades. They are outliers, yes, but outliers are where the revolution begins. In the great cosmic ballet, stars tend to move with a graceful, predictable rhythm. Their spin, brightness, lifespan, all these follow laws that align with mass, age, and environmental conditions. But there are some stars that seem to dance out of step, spinning at incredible speeds, burning with inexplicable energy, or bearing signatures that should not exist in this epoch of the universe. Take, for instance, PSR J1748 22446 AD, a neutron star rotating at an astonishing 716 times per second. Located in the globular cluster Terzan 5, this pulsar holds the record for the fastest known rotation of any star. At this rate, the star's equator is moving at nearly a quarter of the speed of light. It's as if this compact corpse of a massive star has been spun into a blur, defying the limits of material cohesion. How can something so dense, so extreme, hold itself together while spinning that fast? The answer lies in the concept of angular momentum, acquired during the collapse of the original star, but even that has its limits. Theoretical models suggest there's a maximum spin rate before the star would tear itself apart. PSR J1748 22446 AD skirts that boundary dangerously close. Then there are stars that appear too old, not in age per se, but in chemical makeup. In a universe that's 13.8 billion years old, stars should reflect the gradual enrichment of the cosmos with heavier elements, what astronomers call metals. The first stars, called population 3 stars, would have formed from pristine hydrogen and helium, devoid of carbon, oxygen, or iron. These stars should have burned fast and died young, leaving only traces of their explosive ends. But we keep finding stars that seem to carry that ancient primordial fingerprint. Stars like HE 1327 23226, a subgiant star located around 5,000 light-years away in the galactic halo. This star has one of the lowest iron abundances ever recorded, just 1 to 150,000 that of the Sun. It's so primitive in composition that it seems to defy its place in cosmic history. By all accounts, it should have existed billions of years ago, not now. Even more confounding is the suggestion that some of these stars are relatively young, formed long after the Big Bang, but somehow retain the chemical simplicity of the early universe. How could this happen? One theory proposes that pockets of near-pristine gas have remained untouched for billions of years in isolated galactic regions, occasionally forming stars with a chemistry out of step with their age. If true, this would upend our understanding of how metals spread across galaxies over time. In another category entirely are the so-called blue stragglers, stars that seem younger and hotter than the stars around them in old star clusters. Found in ancient globular clusters, where all stars are expected to be roughly the same age, these blue stragglers shine suspiciously bright and blue, suggesting a youthfulness that contradicts their neighbours. One plausible explanation: stellar cannibalism. Blue stragglers may have once been part of binary star systems, where one star siphons mass from its companion, essentially rejuvenating itself by gaining fresh fuel. It's a stellar fountain of youth, but one that requires very specific conditions. The problem is we find more blue stragglers than our models predict, and some of them exist in places where binary interactions shouldn't be common. Once again, the rules bend. On the opposite end of the energy spectrum are the ultra-cool subdwarfs, stars with temperatures so low and compositions so ancient that their existence forces a revision of our timelines. These stars are small and dim, yet they burn with incredible longevity. Some are estimated to live for trillions of years, far longer than the current age of the universe. Their mere presence today suggests we are seeing objects that will one day outlive entire galaxies. And then there are the invisible ones. Stars we know exist not because we can see them directly, but because of their gravitational fingerprints. Dark stars, still a theoretical class, have been proposed as objects that formed in the early universe and are powered not by fusion, but by the annihilation of dark matter particles in their cores. These hypothetical stars would be enormous, cool, and faint, emitting mostly infrared radiation. If discovered, they would not only represent an entirely new category of star, but also provide tangible evidence for dark matter's elusive nature. Astronomers have begun to look deeper into the early universe using instruments like the James Webb Space Telescope. hoping to spot the signature of such an object, a relic from the dawn of time, burning not with hydrogen, but with the energy of the unseen. Then there's the case of magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. A magnetar's field is so powerful it can twist space around it and deform atoms into needle-like shapes. When their magnetic field rearranges itself, it can release bursts of gamma rays and X-rays so powerful that they've been detected from across the galaxy. In 2004, a magnetar located 50,000 light-years away released a flare so strong it momentarily altered Earth's upper atmosphere. How can something so small unleash energy rivaling a billion suns? The answer lies not in fusion, but in the twisting of space-time and quantum mechanical interactions under conditions we can barely simulate. The very existence of magnetars challenges our understanding of matter at nuclear densities and the limits of energy storage in the universe. These stars and objects raise profound questions. How stable is stellar matter under extreme rotation or magnetic stress? How complete is our map of stellar life cycles? Are there entirely new kinds of matter or energy processes waiting to be discovered inside these objects? Science, for all its elegance, is provisional. It adapts. It evolves. And in the case of these stars, the fast-spinning, the ancient, the impossibly strong, it's being pushed to evolve faster. Because each one of these objects is a clue, a missing puzzle piece, a whisper from the universe saying, "You don't know the full story yet." The stars that vanish without a trace. In a universe that prizes persistence, stars are among its most reliable players. They shine for millions or even billions of years, their behavior governed by the elegant balance between gravity and nuclear fusion. But what if a star, burning brightly one day, simply vanished the next? Not in an explosion, not in a dramatic supernova, just gone. That's not science fiction. It's a mystery that's playing out in real time. In 2020, astronomers reported the most baffling case yet of a disappearing star. They had been studying a massive, bright object in the Kinman dwarf galaxy, roughly 75 million light-years away. This star, based on earlier observations, appeared to be a luminous blue variable, LBV, one of the rarest and most unstable types of stars known. LBVs are enormous, highly luminous, and prone to violent outbursts. Think of them as cosmic divas, flaring dramatically, shedding layers of gas, then quieting for unpredictable periods. But the Kinman LBV behaved differently. It didn't flare, it didn't explode. It just vanished from all optical wavelengths. Telescopes that had tracked it for years suddenly saw nothing. No light, no aftermath, nothing at all. There are only two plausible explanations. Either the star went through a dramatic dimming event, obscured by thick dust ejected from its surface, an event so rare it's nearly unprecedented, or it collapsed directly into a black hole, bypassing the typical supernova process entirely. This possibility, though speculative, is gaining traction. Astronomers have long suspected that some massive stars might skip the explosion altogether. Instead of bursting outward in a supernova, their cores collapse silently into black holes, while their outer layers are swallowed in the blink of a cosmic eye. If true, it suggests the universe is hiding countless black holes that were born in quiet stellar deaths, undetectable by anything but their gravity. Another example of such strangeness lies in the ongoing search for failed supernovae. These are stars that reach the end of their fusion lives, but instead of exploding, simply fade. In 2009, scientists launched a project to monitor 27 massive stars in nearby galaxies, watching for the telltale signs of death. Over a decade later, at least one candidate appears to have disappeared with no associated explosion. Just a fading light, leaving behind uncertainty and awe. This raises a profound implication. Our models of stellar death might be missing an entire category of quiet endings. For centuries, we've been enamored by the loud, the explosive, the cataclysmic. But the universe doesn't always follow a theatrical script. Sometimes it whispers. Beyond vanishing stars, we've also encountered those that appear twice. One remarkable case emerged from archived astronomical plates from the 1950s. An object catalogued as a star was observed, then later seen to fade away, and decades later reappear in another set of images. No known natural process fully explains this. Stars don't typically blink out for decades, only to shine again. There's a growing database of such candidates, collectively called WITs, an acronym for What Is This? WITs are objects observed to change drastically in brightness or even vanish entirely without warning. Some fade for months or years, then return. Others seem to be one-time appearances. Some may be related to massive dust ejections, binary interactions, or even gravitational lensing, where light is bent and magnified by an unseen massive object between the star and Earth. But in other cases, no compelling explanation fits. A more exotic hypothesis proposes the presence of black hole binaries, where one star is periodically hidden by its dense partner, or that some of these transient events are powered by interactions with hypothetical objects like boson stars, made of exotic particles that don't behave like normal matter. These objects remain theoretical, but could explain some of the erratic behaviors seen in star-like bodies across the cosmos. In parallel with these observations, there's growing interest in vanishing red giants, old, bloated stars that undergo mass loss episodes so severe they become cloaked in dust and effectively disappear from view. Observations in infrared sometimes reveal their hidden glow, suggesting that what looks like disappearance is really transformation. Still, the sheer suddenness of some cases hints at dynamics we haven't yet unraveled. And while we're still trying to solve these vanishing acts, another layer of mystery is emerging: the discovery of stars with variable surface gravities. Gravity on the surface of a star should be relatively stable, governed by mass and radius. But some stars appear to have changes in surface gravity that can't be explained by simple pulsations or rotation. This hints at unknown internal processes, possibly linked to magnetic instabilities or even unrecognized phases of stellar evolution. What's most compelling about these disappearing and morphing stars is the emotional dissonance they produce. For centuries, we looked up at the sky and thought of it as eternal, unmoving. The stars were fixed points of navigation and wonder. Now we know they flicker, fade, shift, and even vanish, sometimes without a trace. And with every new anomaly, we must revise not only our models, but our mindset. The universe isn't a static canvas of eternal light. It's a dynamic, ever-changing theatre of transformation and illusion. Stars are not immune to mystery. In fact, they may be the greatest source of it. Modern observatories are now equipped with automated systems to detect these changes in real time. Projects like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory are designed to scan the entire sky repeatedly, cataloguing anything that changes, disappears, or flares unexpectedly. These next-generation sky surveys may uncover dozens, even hundreds, of vanishing stars. Each one is a potential revolution, a chance to revise what we think we know about stellar life cycles, gravity, and the physics of collapse. Are we witnessing direct collapse black holes, temporary hiding behind dense exospheres, or something stranger, something that reaches beyond current astrophysical theory? For now, we observe, we catalogue, we wonder. And the stars that vanish remind us, not all endings are loud, not all truths are visible, and not all stars go gentle into that good night. Most stars are born in clusters, nurseries of cosmic gas where hundreds, even thousands of suns ignite and orbit peacefully around the centers of galaxies. Their paths are stable, their homes secure. But not all stars are content with that life. Some are ejected, flung into the darkness, tearing through the galaxy at unimaginable speeds. These are the rogue stars. Homeless, exiled, and wild. To understand why rogue stars challenge everything we know, we must look at their motion. Stars in a galaxy orbit the center in a relatively ordered fashion, like bees around a hive. Their velocities are predictable, but rogue stars, some moving at hundreds or even thousands of kilometers per second, do not follow these rules. They are untethered, hurtling away from the galactic disk, sometimes even escaping the galaxy entirely. The most extreme class of these outcasts are called hypervelocity stars. First theorized in 1988 and confirmed in 2005, hypervelocity stars are believed to be accelerated by interactions with supermassive black holes. If a binary star system ventures too close to the event horizon of a black hole, one star may be captured while the other is ejected at high speed, a gravitational slingshot on a cosmic scale. One of the most famous examples is US 708, a helium-rich subdwarf moving at over 1,200 kilometers per second. It's going so fast that it's not just leaving the Milky Way, it's bound for intergalactic space. Scientists believe it was once part of a close binary system until its companion exploded in a Type Ia supernova, flinging US 708 into exile. This isn't just fast, it's unprecedented, and it's a reminder that stars can be victims of celestial violence. We're only beginning to understand. Even stranger are the so-called intergalactic stars, objects found drifting in the dark voids between galaxies. These stars should not exist where they are. Galaxies are dense with matter, space between them is sparse. How could a star find itself there? One explanation is galactic collisions. When galaxies merge, a common occurrence in cosmic history, tidal forces can eject stars far beyond their original homes. These lone wanderers become castaways of cosmic turmoil, glowing against the blackness of empty space. Though they are dim and rare, their presence speaks volumes about the chaotic forces shaping the universe. But not all rogue stars are speeding away in dramatic fashion. Some are too slow. That's right. Certain rogue stars are moving in odd, meandering paths, far from any galaxy, but without the energy or speed that suggests an ejection. These stars seem to exist in isolation for reasons we can't yet explain. Were they born outside galaxies, in faint intergalactic gas clouds that never coalesced into structured galaxies? If so, that defies current theories of star formation, which rely on dense, gravitationally bound clusters of matter. The discovery of these wandering stars calls into question the fundamental processes of stellar birth. Our models suggest that stars need certain conditions: pressure, density, temperature, metallicity. But these rogue systems hint at alternative pathways, perhaps in low-density environments, or triggered by rare cosmic events, like gamma-ray bursts or dark matter interactions. And then there's the question of how long they can survive. Stars traveling through the galactic halo or intergalactic medium are exposed to environments very different from those inside a galaxy. The interstellar medium provides some shielding: gas, dust, magnetic fields. But in the dark between galaxies, rogue stars are vulnerable to high-energy cosmic rays and micrometeoroid impacts. Their isolation could mean longer lives in one sense, free from dense gravitational perturbations, but it could also mean greater exposure to erosive forces we barely understand. More recently, astronomers have begun to track orphan planetary systems traveling alongside rogue stars. These stars, likely flung from their home galaxies, appear to carry their planets with them, an entire solar system adrift. Imagine a world orbiting a rogue star, with no night sky, no constellations, no Milky Way, just darkness in every direction. It's a haunting image, and a plausible one. The idea of such planetary systems has inspired astrobiologists to rethink habitability. Could life evolve on a planet circling a rogue star? Perhaps with geothermal heat or tidal forces replacing sunlight as the primary energy source. While speculative, such worlds offer tantalizing settings for both scientific speculation and science fiction. Life, if it exists there, would be born in profound isolation, without stars to guide or galaxies to shelter. Some rogue stars, incredibly, appear to move in groups, rogue stellar streams. These could be remnants of ancient dwarf galaxies that were torn apart by the Milky Way's gravity. As their structure was destroyed, their stars were cast into elongated rivers of light, still loosely bound, flowing through intergalactic space. These streams help map the invisible mass of our galaxy, probing dark matter through their distorted paths. Instruments like Gaia, which tracks the precise positions and motions of over 1 billion stars, have been crucial in identifying rogue stars. By analyzing their trajectories, velocities, and origins, we can reconstruct their histories, detecting where they came from, and sometimes what tore them free. Yet even Gaia finds surprises. Some rogue stars have motions that don't match any known event. They don't come from galactic centers. They weren't likely expelled by black holes. Their speed and direction defy expectations. Could there be other forces at work? Some physicists speculate about the role of primordial black holes, tiny ancient remnants of the early universe that could interact with stars and send them flying. Others propose new forms of gravitational wave interactions, or even propulsion effects from hypothetical dark matter halos. While these remain unproven, the very existence of rogue stars demands we keep our minds open. And then, inevitably, we ask, could our sun become one? Unlikely. The sun is deeply embedded in the Milky Way, far from the dangerous gravitational centers that could eject it. But in a far future, as the Milky Way merges with the Andromeda galaxy, billions of stars, including ours, will be flung into new orbits. Some may be thrown out entirely. Rogue stars could become more common, lighting up the cosmic void with stories of gravitational violence and galactic reshuffling. In the end, rogue stars are reminders that not all cosmic journeys are smooth. Not every star stays with its family. Some are torn away, others thrown by violence, and some born to drift. They are the misfits of the cosmos, the exiles, the survivors, the wanderers. And in their lonely paths through space, they carry secrets that no galactic-bound star could ever reveal. Stars that pulse like heartbeats. At first glance, stars appear steady, fixed in brightness, unwavering across centuries. But as we've come to learn, this constancy is an illusion. In reality, some stars pulse and flicker with exquisite regularity. These are the variable stars, and they're not just cosmic oddities. They're keys to unlocking the scale, age, and structure of the universe itself. But buried among the well-understood variables are a class of stars whose rhythms defy current theory. Stars that pulse like heartbeats, but two beats we cannot yet decipher. Let's begin with the more familiar, Cepheid variables. These stars swell and contract in a regular cycle, becoming brighter and dimmer over a period of days to weeks. The period of a Cepheide's brightness fluctuation is directly related to its intrinsic luminosity. This elegant relationship, discovered over a century ago by Henrietta Swan Leavitt, allows astronomers to calculate their distance with remarkable precision. Cepheids are the mile markers of the universe, used to map nearby galaxies and measure cosmic expansion. But not all variable stars play by those rules. Some pulse unpredictably, others defy symmetry. There are stars that flicker violently for no apparent reason, with irregular amplitudes, inconsistent timing, and spectral signatures that don't match any known pulsation model. These are the stars that keep astronomers up at night. Take our Coronae Borealis, for example. This peculiar star spends most of its time shining brightly, then suddenly drops in brightness by several magnitudes, effectively vanishing to the naked eye. It stays dim for weeks or months, then gradually brightens again. The reason? Astronomers believe these stars occasionally belch out thick clouds of carbon dust, which obscure their light. But the process by which this happens is not fully understood. Why the timing is so irregular, why the dust formation is so sudden, and why it happens only in a select few stars. all of it remains mysterious. Then there are the heartbeat stars, a term coined not for sentimentality, but for the shape of their light curves, which resemble the sharp spikes of an electrocardiogram. These stars orbit each other in elongated, elliptical paths. As they near closest approach, their gravitational interaction causes tidal distortions, stretching their outer layers and causing a brief, intense brightening. The result is a dramatic pulse of light, followed by a steady decline, repeating over days or weeks. But some heartbeat stars exhibit additional pulsations between those gravitational peaks, pulses that can't be explained by tides alone. These intermediate flickers suggest that we are witnessing something more subtle, a deep interaction between orbital motion and internal stellar oscillations. In essence, the stars are ringing like bells, resonating in a complex pattern set off by the gravitational rhythm of their dance. These oscillations are the domain of asteroseismology, a field that studies the sound waves rippling through stars. Like earthquakes reveal the internal structure of Earth, stellar pulsations tell us what lies beneath a star's surface. Missions like NASA's Kepler and TESS have uncovered thousands of these oscillating stars, providing detailed insights into stellar cores, rotation, and density. But within this treasure trove of data, scientists have found anomalies. Some stars oscillate in unexpected modes, patterns of vibration that shouldn't be stable, or that don't align with the star's expected size or age. Others appear to switch pulsation modes over time, as if their internal structure is evolving far more rapidly than theory allows. A stunning example of this is KIC 8462852, better known as Tabby's star. While not a traditional variable in the classic sense, Tabby's star exhibits dips in brightness that are irregular, asymmetric, and sometimes profound, up to 22% dimming. That level of fluctuation would require an object dozens of times the size of Jupiter to pass in front of it. No known planet or disk of dust explains the behavior. Various hypotheses have been proposed: collapsing comet swarms, large fragments of planetary debris, but none fit all the data. The mystery of Tabby's star gripped both scientists and the public alike. At one point, speculation even touched on alien megastructures, such as Dyson spheres, not because this was likely, but because natural explanations were so unsatisfying. In time, the dust hypothesis regained favor, but the exact source and structure of that dust remains unclear. We know it's there, we know it's blocking light, but we don't know why it moves the way it does, or where it came from. Another strange case involves rapidly oscillating AP stars, which exhibit unusual chemical compositions, strong magnetic fields, and pulsations that shouldn't coexist in a stable configuration. Their oscillations are often non-radial, meaning different parts of the star's surface move in opposite directions at the same time. This complex internal behavior isn't just unusual, it's a direct challenge to our models of stellar interiors. Why do these stars have surface elements like europium, strontium, and chromium in unusually high concentrations? Why do they pulse in ways that seem chaotic and harmonized at once? Some astrophysicists speculate that the interplay between their magnetic fields and oscillations is key, but current magnetohydrodynamic models can't fully account for the data. And then there are the blinking stars, objects that brighten and dim not in smooth cycles, but in jagged, unpredictable jolts. One such star, catalogued in Kepler data, appeared to pulse for weeks, then stopped completely, then resumed with a different pattern entirely. These sudden transitions suggest internal rearrangements, perhaps helium flash events or abrupt changes in the star's convection processes. It's also possible that we're seeing the effects of external interference, the gravitational influence of unseen companions, planetary debris, or even passing objects from interstellar space. Some theorists have even floated the possibility of cosmic strings, hypothetical topological defects in space-time that could gravitationally lend starlight in unpredictable bursts. While speculative, The mere consideration of such ideas reveals how far these variable stars are pushing the boundaries of astrophysics. They are not just curiosities, they are experimental laboratories, offering rare glimpses into the subtle and complex physics that governs stellar interiors. And yet, the most poetic aspect of these stars is the rhythm itself. A heartbeat, a pulse, a cosmic signal that reminds us that even distant suns can have moods. They breathe, they resonate, they change. They are not the eternal, unchanging lanterns our ancestors imagined. They are alive with motion, with music, with mystery. And the more precisely we measure those flickers, the more we realize these stars are speaking to us in a language we are just beginning to understand, the stars made of strange matter. Most stars we know are composed of familiar ingredients, hydrogen and helium fusing under immense pressure into heavier elements. But there are stars so exotic, so fundamentally different in makeup, that their very existence could rewrite the laws of particle physics. These are the theoretical realms of strange stars, quark stars, and preon stars. Objects made not of atoms, but of matter broken down to its most elemental building blocks. Let's begin at the known edge of stellar collapse, the neutron star. When a massive star explodes in a supernova, the core may collapse into an ultra-dense object made almost entirely of neutrons. A neutron star is only about 20 kilometers wide, but it can weigh more than the Sun. That means a teaspoon of its matter would weigh around 1 billion tons. In these stars, the atomic nuclei have been crushed into a dense fluid of neutrons held together by gravity and neutron degeneracy pressure. But what if the collapse goes further? Beyond the neutron level lies the realm of quarks, the fundamental constituents of protons and neutrons. If the pressure inside a neutron star becomes great enough, it might overcome neutron degeneracy, dissolving the neutrons into a soup of free quarks. This would create a quark star, also called a strange star if it includes a third type of quark called the strange quark. Strange quarks, unlike the up and down quarks that make up everyday matter, are much heavier and only exist under extreme conditions. In a strange star, up, down, and strange quarks are bound together in a fluid known as strange matter. This strange matter could be more stable than normal nuclear matter, meaning once formed it could persist indefinitely, even convert normal matter into strange matter on contact. If this theory is true, then strange stars are not just hypothetical. They might be everywhere, masquerading as neutron stars, but hiding an alien interior. They might be the remnants of some supernovae, or even the product of collisions between neutron stars. In 2002, astronomers detected a compact object named RX J1856.5 to 3754, which at first seemed to be a typical neutron star, but measurements of its temperature and radius didn't quite add up. It appeared too small and too hot. One possible explanation: it wasn't a neutron star at all, but a quark star, an object whose surface and thermal behavior don't match known physics. Quark stars would have extremely smooth surfaces, lacking the crust-like layers of neutron stars. They would also have unusual thermal emissions, no spectral lines, just a nearly perfect black body spectrum. Detecting this is challenging, but future space telescopes may be able to confirm whether these strange signatures exist. And if quark stars push the boundaries of matter, preon stars take us to an entirely different scale. Preons are hypothetical particles, thought to be even more fundamental than quarks. If they exist, and if matter can collapse into a state of preons, then preon stars would be even denser and smaller than quark stars. We're talking about objects the size of a city block with the mass of a star. Preon stars, if real, could be candidates for some of the mysterious dark matter in the universe. Because of their extreme density and small size, they would be almost invisible except through gravitational effects. If one passed through our solar system, we might not notice it, except for the gravitational lensing it might cause to starlight. Of course, preon stars remain purely theoretical. We don't yet have experimental evidence that preons exist, let alone that they can form stable objects. But that hasn't stopped scientists from modeling their properties and exploring how they might be detected through gravitational waves, microlensing events, or high-energy cosmic ray anomalies. Even within the category of known neutron stars, there are outliers that suggest something more is going on. Take the low-mass X-ray binaries, where neutron stars seem to accrete mass from a companion star. Some of these neutron stars appear to grow beyond the expected mass limit, 2.1 solar masses or more, without collapsing into black holes. This could be evidence of an exotic state of matter in their cores, providing additional resistance to collapse. Alternatively, they might not be neutron stars at all, but hybrid stars with a quark matter core surrounded by a neutron star crust. These hybrid stars would have properties of both neutron and quark stars, and could explain the puzzling behavior of high-mass compact objects that don't act like black holes. Another clue may lie in gravitational wave signals. When two neutron stars merge, as seen in the famous Jubadum-Sneen 0817 event detected in 2017, the resulting object should either become a more massive neutron star or collapse into a black hole. But if strange matter exists, the merged object might temporarily form a hypermassive quark star before collapsing. The gravitational wave signal would carry a unique signature, a brief delay before collapse, a sharp peak in frequency, a softer ringdown. Future detectors with higher sensitivity may be able to identify this signature and confirm the presence of exotic matter. The physics of strange stars also has implications for the early universe. If strange matter is more stable than regular matter, then small droplets of it, called strangelets, could have formed during the first microseconds after the Big Bang. These strangelets might still be drifting through space today, invisible and undetectable except through rare interactions with normal matter. If one were to strike a neutron star, it could potentially catalyze a transformation, converting the entire star into strange matter in a matter of seconds. This strange star conversion would be a cosmic contagion, one star infecting another, changing its identity at the most fundamental level. It's a chilling thought, and one that sounds more like science fiction than astrophysics. But it remains a mathematical possibility, and one that astronomers are keeping an eye on. All of this leads to a provocative idea that not all stars are made of atoms. Some may be made of quarks, or preons, or even more exotic matter we haven't yet discovered. These stars would look similar to neutron stars from a distance, dense, dark, pulsing. But their interiors would be alien, filled with particles that do not exist in the ordinary universe. The search for such objects is ongoing. It's a search not just for new stars, but for new physics, new forces, new particles, and new phases of matter that extend beyond the standard model. Because if strange stars are real, then our understanding of matter itself is incomplete. And that means our picture of the cosmos, what stars are, what they become, and what's possible, is still evolving. These stars don't just defy classification, they challenge the foundations of physical law. And if even a single one can be confirmed, it will signal a profound turning point in our understanding of the universe. In the structured universe we've come to know, everything seems to have its place. Spiral galaxies swirl with organized arms. Clusters contain stars of similar age and type. Massive stars form in dense molecular clouds, while smaller stars are scattered throughout the galactic disk. But some stars break this order, not by how they shine or what they're made of, but by where they are. These stars appear in places they shouldn't, at times they shouldn't, acting as if the cosmic rules don't apply to them. One such example is the high-velocity halo star. The Milky Way's halo is a vast, roughly spherical region that envelops the galaxy, containing ancient stars, globular clusters, and dark matter. Most halo stars are old, metal-poor, and cool, relics of the early universe. But every so often, astronomers discover hot, young stars in the halo. stars that, by all accounts, should have formed recently in dense gas clouds that no longer exist in the halo. So how did they get there? Take HE 0437 to 5439, a massive blue star moving away from the Milky Way at over 700 kilometers per second. Its age is estimated at just 30 million years, young in stellar terms. But here's the problem. It's currently located far from any region where star formation occurs, and it's too young to have traveled there from the galactic center by conventional means. It simply hasn't had enough time. It's as if it appeared out there in the emptiness with no stellar nursery to call home. One proposed solution: ejection via interaction with the supermassive black hole at the galaxy's center. In a close encounter between a binary star system and the black hole, one star can be captured while the other is slingshotted outward. That could explain its speed, but its age and location don't quite line up. Some astronomers suggest it was ejected from the Large Magellanic Cloud, a satellite galaxy of the Milky Way. But that also assumes the presence of a massive black hole in the LMC, which remains unconfirmed. Either way, HE's 437 to 5439 challenges our understanding of how stars move, form, and evolve. There are also stars in voids, regions of space utterly devoid of galaxies, gas, or structure. These stars, detected faintly through deep sky surveys, appear to be gravitationally isolated, millions of light years from the nearest galactic structures. Their presence raises difficult questions. Were they flung out during galactic mergers? Are they remnants of long-disrupted dwarf galaxies? Or were they somehow born in isolation, a process that contradicts everything we know about star formation? Star formation, as currently understood, requires dense clouds of molecular hydrogen, triggered by shock waves, cooling, or gravitational collapse. But the intergalactic medium is too sparse and hot to allow this. And yet, we observe these stars, some as part of tidal tails, others floating alone. Their presence implies either past events more violent than we imagined, or mechanisms we have yet to uncover. Perhaps even more intriguing are the runaway O-type stars, massive, hot stars traveling at incredible speeds through the galaxy. These stars typically live fast and die young, burning out in just a few million years. They should be tethered to their birthplace, and yet we find them far from stellar nurseries, racing through the interstellar medium with no clear origin. One famous example is Zeta Ophiuchi, a massive O-type star moving at nearly 30 kilometers per second through space. As it plows through the interstellar medium, it creates a stunning bow shock, an arc of compressed gas and dust shaped like a ship's prow. The most likely scenario is that Zeta Ophiuchi was once part of a binary system. When its companion exploded in a supernova, it was flung outward. But such events are rare, and the number of runaway stars we observe exceeds what our models predict. Some astronomers now speculate that entire populations of massive stars may be kicked from their clusters due to gravitational interactions, like chaotic slingshots, where the most massive star gets ejected during close stellar encounters. Others wonder whether dark matter halos could play a hidden role, exerting subtle forces that nudge stars into strange orbits. In another case of stars where they shouldn't be, astronomers have found metal-rich stars deep within the galactic halo, stars with the chemical fingerprints of younger generations, despite being located in what should be a domain of ancient, metal-poor stars. This suggests some of these stars may have migrated from the disk, thrown outward by galactic bar dynamics or gravitational resonance. Alternatively, they may be interlopers, captured during the Milky Way's past collisions with smaller galaxies. These mergers, which leave behind streams and shells of stars, create messy stellar topography. Stars are scattered far beyond their original homes, creating false impressions of when and where they formed. Still, some of the stars we find appear too out of place, even for merger scenarios. Their velocities, spectra, and ages imply something more. Perhaps remnants of primordial dwarf galaxies that have since dissolved, or even stars ejected during black hole recoil events in galactic centers. Even within galaxies themselves, stars can end up in odd places. Consider the discovery of stars in the intergalactic bridge between the Magellanic Clouds, two satellite galaxies of the Milky Way. This bridge, made of hydrogen gas, contains stars that appear to have formed in situ, despite the low density of material. Their presence suggests that even weak tidal forces between galaxies can trigger pockets of star formation in unexpected places. There are also stars that orbit the galactic plane at extreme inclinations, highly tilted or even retrograde paths, suggesting they were not born in the disk, but captured or scattered into those orbits. Some of these stars may be the descendants of long-dead globular clusters or satellite galaxies, while others may be born from warp-induced disk perturbations, where gravitational interactions bend the disk and scatter its contents. And in the galactic center, the strangest region of all, we find stars that are both too young and too close to the black hole. These are the so-called S-stars, some of which orbit within just a few light hours of Sagittarius A, the supermassive black hole at the center of the Milky Way. Given the extreme tidal forces in that region, star formation shouldn't be possible. The gravitational shear would tear gas clouds apart before they could collapse. Yet the S-stars are there, young, massive, and hot. How they formed remains unknown. Did they migrate inward from farther out? Did they form from compacted disks of gas funneled into the galactic core? Or are they the remnants of disrupted star clusters? Each of these stars represents a problem, a gap in our models, a deviation from the norm that forces us to rethink the rules of stellar behavior. Because space, as orderly as it seems, is shaped by chaos. Mergers, explosions, ejections, and violent gravitational tugs. And sometimes, the stars that we think don't belong are actually the ones telling us the real story of how galaxies evolve. They are not mistakes. They are messengers. The magnetars, stars with supercharged magnetic fields. Among the cosmic oddities challenging our understanding of stars, magnetars stand out as some of the strangest and most powerful. These stellar remnants pack a punch so intense that they defy the conventional limits of magnetic fields, producing phenomena that boggle the mind and push the boundaries of physics. A magnetar is a type of neutron star, the dense core left behind when a massive star explodes as a supernova. But unlike ordinary neutron stars, magnetars boast magnetic fields 1,000 times stronger, around 1014 to 1015 Gauss. To put that in perspective, Earth's magnetic field is about 0.5 Gauss, and a typical refrigerator magnet is about 100 Gauss. The strongest man-made magnets reach a few tens of thousands of Gauss. Magnetars, by contrast, possess magnetic fields so extreme they can distort atomic structures and power bursts of X-rays and gamma rays detectable across the galaxy. The origin of these colossal fields is itself mysterious. It's believed that a rapid rotation combined with convection in the newly formed neutron star amplifies the magnetic field through a dynamo effect, but the exact mechanisms and why only some neutron stars become magnetars remain uncertain. Magnetars don't shine steadily like most stars. Instead, they flare unpredictably. Some emit powerful soft gamma repeater, SGR bursts, sudden releases of energy equivalent to the sun's output over thousands of years, squeezed into seconds. These bursts can disrupt satellites, disturb Earth's ionosphere, and even affect our planet's magnetic environment, despite occurring thousands of light years away. One of the most famous events was the SGR 1806-20 flare in 2004, the brightest cosmic explosion observed since the invention of gamma-ray detectors. Its energy release was staggering, about 1046 ergs, causing measurable effects on Earth's atmosphere. Such outbursts are thought to be caused by starquakes, sudden rearrangements of the magnetar's crust under the stress of its intense magnetic field. Magnetars also exhibit persistent X-ray emission far brighter than expected from simple neutron star cooling, believed to be powered by magnetic field decay. This decay generates heat and powers complex magnetospheres filled with charged particles trapped by the field. Their magnetic fields are so powerful that they warp the very vacuum of space around them, a quantum effect known as vacuum birefringence, altering how light propagates. Observing such effects provides unique tests of fundamental physics in extreme environments. Yet magnetars are fleeting. Their magnetic fields decay rapidly over about 10,000 years, making them young and relatively rare. Our galaxy likely contains only a few dozen active magnetars at any time. Their extreme nature also challenges our understanding of stellar evolution. Why do some neutron stars become magnetars while others become ordinary pulsars? Are magnetars born from more massive stars, or do environmental factors play a role? Adding to the intrigue, astronomers recently discovered magnetar-like behavior in unexpected places. One magnetar candidate was found in a supernova remnant previously thought to host a typical neutron star. Another showed intermittent radio pulsations resembling those of conventional pulsars. These hybrid objects suggest that the boundary between magnetars and other neutron stars may be blurrier than we thought. Even more puzzling, some magnetars exhibit fast radio bursts, FRBs, millisecond-long pulses of radio waves from distant galaxies. The origin of FRBs is one of the biggest mysteries in astronomy. The connection between magnetars and FRBs was dramatically confirmed in 2020 when a magnetar within our galaxy emitted an FRB-like burst, linking these enigmatic signals to magnetar activity. The intense magnetic fields of magnetars may twist and snap, producing the energetic bursts that create FRBs. If so, studying magnetars could unlock the secrets of these cosmic radio signals. Magnetars also highlight extreme states of matter and physics that can't be reproduced on Earth. Their interiors might contain exotic phases of nuclear matter, quark matter, or even more speculative states like color superconductors, a quantum state of quark matter. Magnetars thus serve as natural laboratories for physics at densities, magnetic fields, and energies far beyond human-made accelerators. Understanding them not only illuminates stellar evolution, but also fundamental particle physics. But despite their power, magnetars are elusive. They are dim except during bursts, often hidden by interstellar dust, and identifiable primarily through X-ray and gamma-ray telescopes. Future observatories promise to reveal more about these magnetic monsters, offering insights into their birth, evolution, and demise. Magnetars remind us that stars are not uniform, passive balls of gas. They can become hyperactive, volatile, and terrifyingly powerful, defying the calm, steady glow we often imagine. They show us the extremes to which nature can push matter and energy, and the mysteries still waiting to be unraveled in the stellar zoo. Stars with alien chemistry, the cosmic chemical outliers. When we gaze at the night sky, the twinkling stars may seem uniform in composition, vast spheres of hydrogen and helium, with trace amounts of heavier elements formed through fusion. Yet, within this apparent simplicity lies a hidden complexity. Stars with chemical compositions so bizarre, they challenge the very theories of stellar formation and evolution. These chemical outliers can tell us stories about the life cycles of stars, the history of galaxies, and even the processes that seeded the universe with elements necessary for life. But some stars' chemistries defy explanation. One of the most perplexing classes is the carbon-enhanced metal-poor stars, SEMP stars. These are ancient stars formed in the early universe when heavier elements, metals in astronomical terms, were scarce. Yet, despite their overall metal-poor status, they exhibit unexpectedly high levels of carbon, sometimes thousands of times higher than normal. How can such stars, born in environments devoid of heavy elements, develop such carbon excesses? One hypothesis is that these stars are the survivors of binary systems where a companion star, now a white dwarf, transferred carbon-rich material onto them. Alternatively, some may have formed from gas clouds enriched by the first generation of massive stars, which produced large amounts of carbon through unusual supernova explosions. Even stranger are the magnesium-aluminum stars and S-process enhanced stars, which show surprising abundances of rare elements like strontium, barium, and europium. These elements are typically created in the interiors of evolved stars through neutron capture processes. Finding them in unexpectedly high concentrations, and sometimes in stars that appear too young or too metal-poor to host these processes, forces us to rethink nucleosynthesis pathways. There are also stars with atmospheres dominated by lithium, an element usually destroyed early in stellar interiors. Lithium-rich giants, for example, exhibit lithium abundances far higher than predicted, hinting at internal production or external accretion mechanisms not fully understood. One of the most famous examples is the star Saccharine object, which underwent a late thermal pulse, a sudden reignition of helium fusion after the star had entered its final stages of evolution. This event caused a dramatic change in its chemical composition, including the production of unusual isotopes and dust formation, temporarily transforming its atmosphere and brightness. Another remarkable phenomenon is the discovery of stars with helium-rich atmospheres, such as extreme helium stars, which show almost no hydrogen, the most common element in the universe. These stars may be the products of stellar mergers, where two white dwarfs collide and fuse, resulting in a chemically peculiar object. Even more puzzling are stars exhibiting R-process enhancements, an overabundance of elements created via rapid neutron capture, typically associated with explosive events like neutron star mergers. Detecting such signatures in individual stars suggests a complex chemical enrichment history for their environments, potentially revealing ancient cosmic collisions and explosive origins. Astronomers also study the chemically peculiar AP and BP stars, which display strong magnetic fields and unusual surface element patterns. These stars show excesses or deficiencies of elements like silicon, chromium, and europium in spots on their surfaces, creating stellar weather that changes over their rotation periods. The cause of these chemical anomalies involves magnetic fields altering the movement of charged particles and affecting how elements settle or rise in the stellar atmosphere, a process called atomic diffusion. These mechanisms create patchy element distributions, making the star's light spectra unique fingerprints of magnetic and chemical complexity. Even exotic molecules have been detected in some stellar atmospheres, including carbon chains and silicon compounds, which survive in surprisingly harsh conditions. Chemical outlier stars not only challenge stellar astrophysics, but also enrich our understanding of galactic archaeology. By mapping their compositions and motions, astronomers can trace the assembly history of the Milky Way, uncovering past mergers, star formation bursts, and the dispersal of elements critical for life. Perhaps most intriguingly, these chemical oddities remind us that stars are not simple balls of gas, but dynamic laboratories where physics, chemistry, and time intersect in bewildering ways. They tell us that the universe's recipe book is far more complex than once thought, and that every star, even one that looks ordinary to the naked eye, may harbor secrets that rewrite cosmic history. Stars that spin at impossible speeds. Spin is fundamental to stars, from their birth in rotating clouds of gas and dust to their mature lives balancing gravity and centrifugal force. Stellar rotation shapes their structure, evolution, and even fate. But some stars spin so fast they defy what our physics predicts, pushing the limits of stability and challenging our understanding of angular momentum in the cosmos. Most stars rotate at moderate speeds. Our Sun completes a rotation roughly every 12 days at the equator, but some stars spin dozens or even hundreds of times faster. Take the class of B stars, hot, massive stars characterized by rapid rotation, often close to their critical breakup speed, where centrifugal forces threaten to tear them apart. These stars frequently eject material into surrounding disks, producing emission lines that give them their E designation. Their extreme spin causes significant equatorial bulging, leading to temperature gradients and complex surface phenomena. But even B stars can be outpaced. The fastest spinning stars are neutron stars, stellar corpses left behind after supernova explosions. Many neutron stars rotate hundreds of times per second, known as millisecond pulsars. These exotic objects spin so fast because they have been recycled by accreting matter from a companion star, gaining angular momentum in the process. Their rotation periods can be as short as 1.4 milliseconds, a dizzying 700 revolutions per second. At such speeds, neutron stars flatten due to centrifugal force and produce beams of radiation detectable as pulsars. But even these rapid rotations are constrained by physics. Spin faster, and the star would break apart or shed mass. Then there are the enigmatic hypervelocity rotators, stars observed to spin near or above theoretical breakup velocities, yet somehow maintaining cohesion. Such stars pose a paradox. Standard models predict these stars should lose mass rapidly or explode, but they persist. One explanation lies in magnetic fields and internal angular momentum transport. Magnetic braking slows rotation over time, while turbulent viscosity redistributes spin within the star. But for some stars, these mechanisms appear insufficient. Recently, astronomers discovered a subset of stars with extreme rotational mixing, where rapid spin induces internal flows that bring nuclear-processed material from the core to the surface. This challenges the traditional layered structure of stars and impacts stellar lifetimes, luminosities, and supernova progenitor models. In particular, massive stars in the Wolf-Rayet phase often exhibit fast rotation and strong stellar winds. Their spin can strip outer layers, revealing heavier elements and altering their evolutionary paths. The fastest known spinning star is VFTS 102, located in the Large Magellanic Cloud, which spins at a velocity near 600 kilometers per second, around 90% of its breakup speed. Its rapid rotation likely results from mass transfer in a binary system, and it may be on course to become a gamma-ray burst progenitor. Gamma-ray bursts, GRBs, are the most energetic explosions in the universe, and their connection to fast-rotating massive stars is a cutting-edge area of research. The collapsor model suggests that when such a star's core collapses, rapid spin powers jets that produce GRBs. Understanding how stars maintain such extreme rotation is vital not just for stellar physics, but also for high-energy astrophysics and cosmology. Rotation also influences stellar magnetism. Fast rotators often generate strong magnetic dynamos, impacting stellar winds, mass loss, and angular momentum evolution. The interplay between spin and magnetism can lead to phenomena like star spots, flares, and coronal mass ejections. Effects with implications for exoplanet environments. In some cases, rotation drives exotic pulsation modes and gravity waves within stars, detectable through asteroseismology. These internal waves transport angular momentum and energy, potentially affecting star lifetimes and end-of-life behavior. But spinning stars aren't just fascinating individually, they also tell us about the dynamics of their birth environments. Rapid rotation often results from interactions in dense star clusters, binary mass transfer, or stellar mergers. Thus, spin distributions provide clues to star formation history and binary evolution. Finally, theorists ponder the limits of stellar spin. Could a star spin fast enough to break apart completely? Would it shed mass to maintain stability? Could it form a disk or rings like planets? Nature's fastest rotators provide a natural laboratory for exploring these extremes. They challenge our understanding of physics under conditions impossible to recreate on Earth. They reveal a universe where stars do not simply shine. They whirl, twist, and dance on the edge of destruction. And in doing so, they show us that even the oldest, most familiar cosmic objects can surprise us with their wild extremes. Rogue stars, wanderers without a home. In the vast cosmic ocean, most stars are tethered by gravity to galaxies, clusters, or binary companions. Yet, some stars break free, becoming rogue stars, lonely travelers wandering interstellar or even intergalactic space without any permanent home. These stellar vagabonds defy expectations, raising profound questions about how stars move, interact, and survive outside the protective embrace of their stellar families. Rogue stars can be born through several dramatic processes. One of the most common involves gravitational ejection. In dense star clusters, close encounters between multiple stars or binaries can sling one star out at high velocity. Sometimes, a supernova explosion in a binary system tears apart the pair, flinging the surviving star into deep space at hundreds of kilometers per second. Astronomers have identified many such hypervelocity stars, racing through the Milky Way's halo at speeds sufficient to escape the galaxy's gravitational pull altogether. These stars may eventually become intergalactic nomads, drifting forever in the dark between galaxies. One of the first confirmed hypervelocity stars, SDSS J090745.0-24507, was discovered in 2005, moving at over 850 kilometers per second, fast enough to leave the Milky Way. Its origin is traced back to a gravitational interaction near the supermassive black hole at our galaxy's center. Such ejections highlight the dynamic and sometimes violent nature of galactic cores. Yet not all rogue stars owe their status to black hole slingshots. Some are expelled by complex gravitational dances within young star clusters, where tight groupings of massive stars interact chaotically. These interactions can hurl stars into the galactic halo, where the density of gas and dust is low, making further star formation unlikely. Rogue stars challenge our understanding of stellar life cycles. How do stars survive in the cold, sparse environments far from galactic disks? Without the steady influx of interstellar gas, they cannot replenish mass lost to stellar winds. Their isolation also means fewer chances of forming planetary systems or interacting with other stars. Despite their lonely journeys, some rogue stars shine brightly. Those that are young and massive continue fusing fuel, but their isolation makes them rare and hard to find. More commonly, we detect old, low-mass rogue stars, faint and difficult to observe. Detecting these wanderers requires large sky surveys and precise astrometry to track their motions against the celestial background. The European Space Agency's Gaia mission has revolutionized this field by mapping the positions and velocities of over 1 billion stars, identifying candidates for rogue or hypervelocity status. Some rogue stars are accompanied by exotic companions. Recent discoveries include hypervelocity binary stars, pairs ejected together at high speeds. These systems defy simple explanations and suggest complex formation scenarios, possibly involving multi-body gravitational interactions near black holes. In addition to stars, rogue planets also roam the galaxy, unbound from any star. These planetary wanderers may have been ejected during early system formation or born in isolation from collapsing gas clouds. The existence of rogue stars and planets broadens our conception of what it means to belong in the cosmos. Not every object is part of a stable system. Many live lives of transient movement, shaped by chance encounters and violent events. The interstellar medium through which rogue stars travel is harsh and sparse. Without dense gas clouds to interact with, these stars slowly lose mass through winds and radiation. Their long-term evolution may differ from their galactic counterparts. Understanding rogue stars informs galactic dynamics, stellar evolution, and the processes that shape the architecture of galaxies. Some speculate that rogue stars might be responsible for some of the mysterious intergalactic light detected between clusters, diffuse glows unaccounted for by known galaxies. Furthermore, rogue stars could be vital in spreading heavy elements beyond galactic boundaries, enriching intergalactic space over cosmic timescales. Their journeys are lonely but not meaningless. Rogue stars are cosmic drifters, defying the bonds that hold most stars in place. They remind us that the universe is vast and dynamic, where even stars can be wanderers, embracing uncertainty as they traverse the dark. In star clusters, where stars are born from the same cloud at roughly the same time, astronomers expect a predictable pattern. The most massive stars burn through their fuel quickly and die early, leaving behind a population of aging, cooler stars. Yet hidden among these ancient stars are the blue stragglers, stars that appear inexplicably young, hotter, and more luminous than their peers. Blue stragglers stand out like rebels defying the clock, straggling behind in the evolutionary race. They shine with the blue hue of youth, despite residing in environments dominated by much older stars. Their presence has puzzled astronomers since their discovery in the 1950s, forcing a re-evaluation of stellar aging and interactions. The prevailing explanation involves stellar collisions or mass transfer in binary systems. In dense cluster cores, stars can collide or merge, rejuvenating themselves with fresh hydrogen fuel. Alternatively, a star in a close binary may siphon material from its companion, gaining mass and appearing younger. Both processes challenge the assumption that stars evolve in isolation, highlighting the complex social lives stars lead in crowded environments. Blue stragglers provide a living laboratory for studying stellar dynamics, binary evolution, and cluster physics. Their properties offer clues about how stars interact gravitationally, exchange mass, and influence each other's destinies. However, not all blue stragglers fit neatly into these scenarios. Some show chemical abundances or rotation rates inconsistent with simple merger or accretion models, suggesting alternative or multiple formation channels. Intriguingly, blue stragglers appear not only in globular clusters, but also in open clusters and even in the galactic field, indicating their formation is widespread and varied. Studying blue stragglers also has implications for measuring cluster ages and understanding the evolutionary history of galaxies, since their presence can bias age estimates based on stellar populations. Beyond their youthful appearance, blue stragglers sometimes display unusual pulsations, magnetic activity, or variable brightness, indicating that their internal structures differ from standard stars. The mystery of blue stragglers embodies the theme of this documentary, stars that don't fit the rules, pushing us to deepen our understanding of how the universe works. They remind us that stellar evolution is not just a simple countdown, but a complex dance influenced by companionship, chance encounters, and cosmic violence. Among the many cosmic oddities, a class of objects known as ultraluminous X-ray sources, ULXs, defy expectations by shining with X-ray luminosities exceeding 1,000,000 times that of typical stellar X-ray sources. These extraordinary objects blur the line between stellar remnants and supermassive black holes, raising fundamental questions about how such intense energy can be generated on such a scale. ULX are usually found in star-forming regions within galaxies, and their luminosities are far too high to be explained by typical neutron stars or black holes accreting matter at standard rates. Instead, they suggest either unusually massive black holes or exotic accretion physics. Some ULXs are thought to be intermediate mass black holes, IMBHs, with masses between hundreds and thousands of solar masses, forming a bridge between stellar mass black holes and the supermassive giants lurking in galactic centers. However, definitive proof of IMBHs remains elusive. Alternatively, recent observations reveal that some ULXs are neutron stars with extreme magnetic fields and accretion rates, pushing physics to its limits. The discovery of pulsations in certain ULXs confirmed their neutron star nature, forcing a rethink of how much energy such small objects can emit. The accretion disks around these compact objects, where gas spirals inward, are thought to produce powerful X-rays through intense heating. In ULXs, the accretion rates may surpass the Eddington limit, the theoretical maximum luminosity a star or black hole can have before radiation pressure halts further infall. How ULX maintains such super Eddington accretion is a topic of active research. Some models propose that strong magnetic fields funnel inflowing matter onto the poles of neutron stars, concentrating the energy output and allowing luminosities far beyond standard limits. ULXs also exhibit spectral states and variability unlike typical X-ray binaries, with complex timing and energy characteristics hinting at unique accretion physics. Their extreme energy output can affect the surrounding environment, generating X-ray ionized nebulae and influencing star formation in their host galaxies. ULXs challenge the simple dichotomy of black holes and neutron stars, revealing a continuum of accretion and energy release mechanisms that push the boundaries of astrophysics. They also serve as laboratories for studying extreme gravity, magnetic fields, and radiation physics in ways impossible on Earth. Despite their power, ULX remain relatively rare, detected in only some galaxies, and their exact nature varies widely. Understanding ULXs is key to unraveling the complex life cycle of massive stars, compact objects, and the growth of black holes. They shine as cosmic lighthouses, warning us that stars and their remnants can behave in astonishing, unexpected ways. The pulsating stars, rhythms that defy expectations. Among the many ways stars surprise us, their rhythms stand out. Stars don't just shine steadily, many pulsate, expanding and contracting in cycles that can range from minutes to years. These pulsations reveal hidden layers of physics within stars, yet some stars pulse in ways that challenge our understanding. The most famous class are Cepheid variables, whose rhythmic brightness variations serve as cosmic yardsticks for measuring galactic distances. Their pulsations follow well-understood patterns tied to their size and luminosity. Yet, there exist stars with pulsations so irregular, rapid, or multi-periodic that they defy conventional models. For example, RR Lyrae stars pulse with periods of less than a day, marking them as older, low metallicity population stars. Their pulsations have been invaluable in mapping the structure of the Milky Way. But beyond these lie more enigmatic stars like the Zizi Ceti stars, white dwarfs exhibiting non-radial pulsations. These tiny, dense stars vibrate in complex patterns, revealing internal structure through asteroseismology. Yet, some ZZ Ceti stars show unexpected modes or amplitude changes that puzzle theorists. Similarly, slowly pulsating B stars display gravity mode pulsations that test models of stellar interiors and rotation. Their pulsations can change over decades, suggesting evolving internal processes not fully captured by current physics. Even stranger are heartbeat stars, binary systems whose orbits cause tidal forces that distort and pulsate the stars at each closest approach. Their complex pulsation patterns reflect interactions between gravity, rotation, and stellar structure. Adding to the mystery, some stars undergo sudden pulsation changes or mode switching, phenomena that remain poorly understood. Pulsations also occur in highly magnetic stars, where magneto-hydrodynamic forces interplay with oscillations, producing complex variability. Understanding these rhythmic outliers pushes the frontier of stellar physics, enabling us to probe conditions deep inside stars, test theories of convection, magnetism, and rotation, and refine models of stellar evolution. The study of stellar pulsations has become a cornerstone of modern astrophysics, linking observations with theory to unlock the secrets of stars' inner lives. These pulsating stars remind us that stars are dynamic, living systems, not static spheres of plasma. Their rhythms tell tales of turbulence, energy flow, and cosmic timekeeping that we are only beginning to understand. They reveal that even the steady light we see in the night sky is often a complex symphony of motion and change. Beyond the well-known types of stars and stellar remnants, theoretical astrophysics proposes exotic objects that push the limits of matter itself. Among these, quark stars stand as one of the most fascinating and mysterious candidates. Hypothetical remnants denser than neutron stars, composed of free quarks rather than neutrons. To understand quark stars, we must first revisit neutron stars. When massive stars explode as supernovae, their cores collapse under gravity. Protons and electrons merge to form neutrons, creating a dense neutron star, an object packing the mass of the Sun into a sphere roughly 20 kilometers across. However, at even higher densities, some theories predict that neutrons themselves may dissolve into their constituent quarks, creating a quark-gluon plasma, an exotic state of matter where quarks are no longer confined inside neutrons or protons. A quark star would be composed mostly of this deconfined quark matter, sometimes referred to as strange quark matter if it contains strange quarks alongside up and down quarks. Quark stars, if they exist, would be smaller and denser than neutron stars, but not massive enough to collapse into black holes. Their existence is still theoretical because no definitive observational evidence has yet confirmed their presence. But several candidates have been proposed based on unusual X-ray and gamma-ray observations. One of the main challenges in detecting quark stars is that their properties could closely resemble neutron stars, requiring precise measurements of mass, radius, and cooling rates. Quark stars could explain certain anomalous observations, such as extremely compact stars with rapid cooling, or unusual surface temperatures inconsistent with neutron star models. Their surfaces might be bare quark matter, or have thin crusts, affecting their radiation and interaction with magnetic fields. The possibility of quark stars opens a window into quantum chromodynamics, QCD, under extreme conditions, a realm impossible to recreate in terrestrial laboratories. Studying quark stars could test fundamental physics about the strong nuclear force, the behavior of matter at supranuclear densities, and the phase diagram of QCD. Astrophysical events like mergers of neutron stars, observed via gravitational waves, and electromagnetic counterparts, may offer clues about quark matter creation or phase transitions inside dense stars. Future missions aiming to measure neutron star radii and masses with unprecedented precision, such as the NICER experiment on the International Space Station, could help distinguish quark stars from neutron stars. If quark stars exist, they might also have implications for fast radio bursts, FRBs, and other high-energy transient phenomena, possibly linked to exotic processes in their interiors. While speculative, the study of quark stars epitomizes the quest to understand how matter behaves when pushed beyond known limits. It challenges our conception of what a star can be and hints at hidden layers of complexity beneath the surface of the cosmos. The dark stars, hypothetical beacons powered by dark matter. While most stars we observe burn by fusing hydrogen and heavier elements in their cores, some theoretical models predict the existence of dark stars, objects that could have existed in the early universe, powered not by nuclear fusion, but by the annihilation of dark matter. Dark matter, which makes up about 27% of the universe's mass-energy content, remains one of the greatest mysteries in cosmology. It interacts gravitationally but emits no light or radiation, making it invisible to traditional telescopes. Yet, it may interact weakly with itself, allowing for annihilation that releases energy. In regions of dense dark matter concentration, such as the early universe's first star-forming halos, dark matter particles could accumulate in protostellar clouds. Instead of collapsing directly into hot nuclear-fusing stars, these clouds could be heated by the energy from dark matter annihilation, halting collapse and forming a dark star. These stars could grow to immense sizes, thousands or even millions of times the mass of our Sun, because dark matter heating could sustain their size and prevent the rapid onset of fusion. Unlike fusion-powered stars, dark stars would be cooler and larger, shining predominantly in the infrared. They could have lifetimes lasting millions to hundreds of millions of years, longer than conventional massive stars. Detecting such stars today is challenging, but some argue they might have left indirect signatures in the cosmic microwave background or in the distribution of early galaxies. If dark stars existed, they would fundamentally change our understanding of the first luminous objects, cosmic reionization, and the evolution of the early universe. Their eventual collapse might have seeded the formation of supermassive black holes, explaining how such giants formed so early in cosmic history. Though no direct evidence of dark stars exists, future telescopes like the James Webb Space Telescope may find clues in the earliest epochs of star formation. The idea of dark stars highlights how much remains unknown about star formation in the primordial universe and how exotic physics could shape cosmic structures. They represent a bridge between astrophysics and particle physics, linking the largest cosmic scales to the smallest building blocks of matter. Dark stars remind us that not all stars burn with familiar fire. Some may shine with the hidden energy of the universe's dark side. Among the most colossal stars known are the hypergiants, stellar behemoths that push the boundaries of size, luminosity, and stability. These giants, far larger and brighter than typical supergiants, challenge our understanding of how stars hold themselves together under extreme forces. Hypergiants are rare and short-lived, often unstable stars with masses ranging from 30 to over 100 times that of the Sun, and luminosities reaching millions of times solar output. Their immense energy production causes powerful stellar winds that strip mass at astonishing rates, sometimes equivalent to the Sun's mass over just a few thousand years. One famous example is Eta Carinae, a luminous blue variable, or LBV, hypergiant, located about 7,500 light-years away. Eta Carinae has experienced massive outbursts, including the Great Eruption in the 19th century, during which it briefly became one of the brightest stars in the sky. During such events, it shed several solar masses of material, creating the spectacular Homunculus Nebula. The existence of hypergiants presents challenges for models of stellar structure. Their enormous radiation pressure nearly balances the inward pull of gravity, pushing these stars to the brink of instability. The mechanisms that govern their mass loss and prevent them from exploding prematurely remain areas of active research. Hypergiants also show significant variability in brightness and spectra, linked to pulsations, eruptions, and changes in their dense stellar winds. These variations complicate the task of accurately measuring their properties and understanding their evolution. Their ultimate fate is dramatic. Hypergiants are expected to end their lives as supernovae, or even hypernovae, potentially leaving behind neutron stars or black holes. They may also be progenitors of long-duration gamma-ray bursts, some of the universe's most energetic explosions. Studying hypergiants sheds light on the upper mass limits for stars, the physics of extreme radiation pressure, and the processes driving mass loss in massive stars. Moreover, their intense winds enrich the interstellar medium with heavy elements, influencing subsequent star formation and galactic chemical evolution. Despite their importance, hypergiants are poorly understood due to their rarity, distance, and instability. Observations across the electromagnetic spectrum, from radio waves to X-rays, are required to piece together their complex behavior. Future instruments and surveys promise to reveal more hypergiants in our galaxy and beyond, helping us map the extremes of stellar evolution. Hypergiants exemplify stars that go against everything we know: too large, too bright, too unstable, yet resilient and awe-inspiring beacons in the cosmos. They challenge theories and captivate astronomers, standing as monuments to the power and complexity of stellar physics. In the cosmic dance of stars, pairs bound by gravity are common, but some binary systems push the limits of what we understand about stellar interaction, evolution, and behavior. These exotic binaries feature stars that defy norms individually, and together they create phenomena that challenge our models and ignite scientific curiosity. One fascinating example is the class of X-ray binaries, systems where a compact object, either a neutron star or black hole, accretes matter from a stellar companion. The accretion process releases tremendous energy, often in X-rays, making these binaries among the brightest X-ray sources in the sky. Within this class, microquasars exhibit relativistic jets, streams of matter accelerated to near-light speeds by the compact object's intense gravity and magnetic fields. These jets mimic the behavior of quasars, supermassive black holes at galactic centers, but on a smaller scale, providing a laboratory for studying jet physics and accretion dynamics. Another exotic binary type is the cataclysmic variables, CVs, where a white dwarf pulls material from a nearby companion. Accumulation of matter on the white dwarf surface can trigger thermonuclear runaways, causing novae, dramatic brightening events visible from Earth. Recurrent novae, systems undergoing multiple eruptions, further complicate the picture of mass transfer and ignition. Some binaries contain two compact objects in close orbit, such as double neutron star systems or black hole binaries. These pairs in spiral due to gravitational wave emission, eventually merging in cataclysmic events detected by observatories like LIGO and Virgo. These mergers produce bursts of gravitational waves and electromagnetic radiation, revealing new astrophysical phenomena and testing general relativity. Among the most puzzling binaries are those with extreme mass ratios, where a massive star or black hole orbits a much smaller companion. Such disparities lead to complex tidal interactions, mass transfer episodes, and orbital evolution that defy simple prediction. There are also binaries where stars exhibit tidal locking, distorted shapes, and synchronized rotation, altering their magnetic activity and evolutionary paths. Binary interactions can spin up stars to near breakup speeds, trigger enhanced magnetic fields, or cause envelope stripping, producing unusual stellar types like stripped envelope stars or blue stragglers. In rare cases, binary stars merge completely, forming single stars with unusual properties, such as high rotation or peculiar chemical abundances, further complicating the classification. The diversity of exotic binaries reflects the complex interplay of gravity, magnetism, radiation, and fluid dynamics on stellar scales. They are laboratories for studying extreme physics, from accretion disks and jets to nuclear burning and gravitational waves. Understanding these systems informs broader topics like stellar population synthesis, galaxy evolution, and the origin of heavy elements.